Hello everyone, my name is Akiba, and I did my final project on whether total domination of the volleyball court can be achieved by the knowledge of fluid mechanics. All right, so the volleyball action that I chose to investigate further is the volleyball serve. And the reason is because, as you can see from this short video clip, a really good volleyball serve right to the baseline of the other court, the defender really can't do anything about that to stop them. So to achieve domination, total domination of the volleyball court, I thought that it would be best to optimize the volleyball serve first. Okay, so let's take a look at the types of volleyball serves that were taken into account for our project. So the four serves that were taken into account were the underhand, the standing floater, the jump floater, and the jump topspin serves. To characterize the fluid problem a little bit better, here I've drawn a free body diagram. And so the three forces that are acting on a spinning volleyball is the gravity, Magnus force, and the drag forces. So let's talk about the drag forces and the Magnus forces a little bit more. As far as the drag force goes, first of all, we need to sort of come up with a comparison of the quadratic to linear drag. So here we've taken the ratio, and it turns out that the ratio calculates to around 10 to the 3 or 10 to the 4. So we are justified to try to neglect the linear drag and talk about the drag force with this particular equation shown here, where there's a quadratic dependence on the velocity. Now, one non-dimensional number that is really important in our system is the Reynolds number, the ratio between the inertial forces and the viscous forces. And in this system, this is a very high Reynolds number system with 10 to the 5. And it turns out that the drag coefficient is actually a function of the Reynolds number, as shown in the right here on the figure. So this is the first effect that was taken into account, is the drag force of the system. The second effect that is important for specifically our jump topspin serve is the Magnus effect. So when the ball is spinning, this adds an additional force that is perpendicular to the direction of motion. One equation for the Magnus force, it can be written as shown here. And you can easily verify that for a jump topspin serve. This means that the Magnus force is pointed downward, and you can easily verify that by using the right-hand rule. And according to Adair and Giordano, a good approximation for a sphere is this value of the factor S in the front shown. So this is what we've used for our trajectories. So how are the trajectories affected by these forces? So shown are comparisons for the jump topspin serve trajectories, but the gravity one is shown in green, so that's without the effects of anything else. The orange is gravity plus the force of drag. And finally, the blue takes into account all three forces: gravity, drag, and the Magnus force. So using each of the relevant forces in each of our serves, we've generated optimized trajectories, which we will now show. So for the underhand serve, this is an animation that shows the optimized trajectory, just going over the volleyball net and landing at the baseline. Here's the standing floater serve animation. Next, we have the jump floater serve animation. And finally, we have our jump topspin serve animation. And all of these animations that I've shown are real time. So this is how fast the ball will be going in actual volleyball court. Okay, and here are the comparisons between the different optimized trajectories. And you'll notice that we have used different initial conditions depending on each of the serves and where the balls are released. But because we want to make quantitative comparisons as well, here I've shown in a table the initial speed of the ball and the inclination angle that the ball is released from with the horizontal. So you'll notice that as we go towards the jump serves, we can release the ball at a faster speed and at a lower inclination angle, which makes sense because they start at a higher point. And we have also shown in the table the effects that were taken into account in each case. Okay, the final thing we're going to talk about is the knuckleball effect, which wasn't taken into account in our models, but is also important in our sport of volleyball. So this is the zigzagging, unpredictable motion when the ball has no spin. So it's especially important for the floater serves. This was first seen in baseball, and that's where the name knuckleball comes from, but now is widely used in many other sports, including volleyball. And the cause is said to be the asymmetries of the ball. So for example, for the baseball, the seams would be the asymmetries. And for the volleyball, same thing. There's slight asymmetries in the surface of the ball that is causing these deviations from calculated trajectories. And Texier et al. Has seen deviations of up to 1.5 or so volleyball diameters in numerical simulations. So in conclusion, yes, theoretically, I can dominate the volleyball court by producing the optimized trajectories every time, but in reality, sadly, I probably can't. And based on the optimized trajectories, jumping serves are significantly better. So no wonder that the top professional volleyball players usually switch between the two jump serves. The world record, though, for the fastest volleyball serve was 37 meters per second, or 84 miles an hour. And this is ridiculous, and I can't even model that sort of initial speed by using my optimized trajectories. So as a personal reflection, I need a higher vertical and more topspin on my serves. So thank you. And here are my references.